Hi everybody. Today we are going to talk about how you can use the Trenza Survey Performance tool to create a profile of your HPC application and identify approaches that may be able to make your runs more efficient. Survey is an HPC performance tool from all of us at Trenza Synergy. This presentation is based on work we did with the Department of Energy National Laboratory in assisting them with the acceptance of a new supercomputer. The supercomputer in question is a Cray EX supercomputer with Cray Shasta architecture using Sapphire Rapids nodes with 2 sockets per node and 56 cores per socket for a total of 112 physical cores per node. These 112 physical cores equal 224 logical cores. This figure, generated from the lstopo command, shows the topology of the system. Each of the 2 sockets has 4 NUMA domains for a total of 8 NUMA domains per node. The 112 physical cores are divided into these 8 NUMA domains for a total of 14 cores per NUMA domain. The number of physical cores on a node, 112, is a very inconvenient number if your preference is to select powers of 2 for the number of MPI tasks or OpenMP threads. It can make the task of utilizing all the cores efficiently more complicated. The closest power of 2 that doesn't exceed the number of cores is 64, which, if selected, would barely use half of the cores. Additional complexity that a user must be knowledgeable to optimally use this architecture are core specialization, 2 different memory options, that's DDR4 or HBM, and a choice of programming environments, Intel, Cray, and GNU. All of this means that to use this machine efficiently, you really need to have a good understanding of the performance bottlenecks before you undertake production runs. Trenza Survey will help you achieve this by providing you with a high-level profile of the application runtime components. In this video, we will illustrate the use of Survey with application runs and give you some ideas of how you can use this information for improving the performance of your own runs. In our first example, we show how the performance of an application can be adversely affected by not paying attention to how MPI ranks and OpenMP threads are mapped to the node cores. We are using the snap benchmark on one node with 56 MPI tasks and 2 OpenMP threads per rank. Here are the Affinity results provided by Survey when we run the application with pedestrian srun options. Notice how cores 0 and 112 are both assigned to the 2 threads of rank 0. Remember that on this system there are only 112 cores per node. So core 112 actually corresponds to a logical core with the same physical core as core 0. That means the physical core is oversubscribed. The other cores are similarly oversubscribed. Now let's see the results of the same benchmark run with carefully chosen srun options. Cores 0, 1, 112, and 113 are all subscribed to rank 0. Cores 0 and 112 belong to one physical core, while cores 1 and 113 are on a different physical core, giving each OpenMP thread of rank 0 its own physical core. Now let's look at the runtimes. The first run with the oversubscribed cores took 38.9 seconds to run. The second run, in which each rank is assigned 2 different physical cores, took 19.18 seconds to run. That's about half the time as the previous run. Not paying attention to the affinity can have a significant impact on the performance of your application. This next example shows how we can use survey results to measure improvements in time spent in MPI calls using application builds with alternative page sizes. Studies have shown that large page sizes improve MPI communication times when there is heavy MPI message traffic. Survey has the capability to show an extended MPI profile in addition to the basic measurement of time spent in total MPI calls, giving us the information needed to identify applications with high MPI message traffic. Here's some of the results from the P3D FFT benchmark when it was built with the default page size of 4K. From the survey results, we can see the dominant MPI call is MPI allgather V. There were 44 calls and a total of about 14 gigabytes, which makes this application very communication heavy. This is the nature of the 3D FFT algorithm that requires a corner turn for the second and third dimension of the data array. If we divide the number of bytes in the all-gather call, that's 14 gigabytes, by the number of calls, that's 44, and the number of ranks, that's 220, we get 1.44 megabytes for each communication. The total MPI time for these calls is 156.23 seconds. Here's the results from the benchmark. This time the application is built with a module that uses large page sizes of 2 megabytes, a size larger than each all-gather message. The total MPI time is now 137.04, a reduction of 12.3% in the overall runtime. Although this may not seem very significant, when multiplied by a run on thousands or even tens of thousands of nodes, this performance increase will add up quickly. In this next example, we will use the Survey extended MPI measurements to profile the application and identify potential performance improvements. Here are the results of the SNAP benchmark run on 12 nodes with 336 MPI tasks. As you can see, this benchmark has a large amount of communication between its nodes. Applications like this can benefit from reordering the MPI ranks in order to maximize the efficiency of the message passing so that a large volume of messages are passed within nodes rather than between different nodes. CRAPEP provides a procedure for generating a more efficient MPI rank order, giving an MPitch rank order file that is used in conjunction with an environmental variable setting MPitch rank reorder when the application is run again. Here are the results after the MPI rank reorder has been invoked at runtime. Notice the performance improvement from 417 seconds to 383 seconds, nearly a 9% decrease in runtime. And we have seen improvements of up to 2 times when using this feature on runs of thousands of nodes. This next example was run with the SNAP benchmark. Here are the outputs of a strong scaling study using 12, 24, and 48 nodes with 336, 672, and 1,344 MPI tasks respectively. Each run is set up to use 28 MPI tasks per node. In a strong scaling study, we use the same input but change the number of nodes to see how the runtime and memory allocation change as the number of nodes increase. When a fewer number of nodes are used in the same input, the amount of memory used per task increases. Survey output shows that in a 12-node run, the DMEM high water mark is 8 gigabytes. Now, with 28 nodes and 8 gigabytes per node, that's about 224 gigabytes, which is approaching the memory capacity of the node. We can conclude that using fewer than 12 nodes with the same input will lead to an out-of-memory error, that is OOM. A subset of the PAPI hardware counter metrics collected as a total during the entire run of the application are listed in the survey output. Although PAPI counter values are usually large numbers difficult to interpret, a few of the derived metrics, that is, ratios of 2 counters, may be particularly useful to software developers to find performance bottlenecks in their code. Here's an example of how the survey PAPI derived metrics like instructions per cycle or computational intensity can be useful. As you may know, using structures of arrays, that is SOA, instead of array of structures, that is AOS, is often better for contiguous memory access and vectorization. Here's a contrived example demonstrating this concept using survey. In a simple benchmark that uses AOS and SOA to count the number of points within a unit sphere among 100 million random points in 3D space. Here are the results using an array of structures, AOS. And here are the results using a structure of arrays, SOA. The SOA has a 16% better performance. Notice the difference in the instructions per cycle, that is the number of instructions divided by the total number of cycles, and the computational intensity, that is the number of cycles divided by the number of instructions. These derived metrics may serve as a good indication of the overall efficiency of the algorithms in your application. And that is the end of the examples in this video. I hope this video both informed and motivated you to see if the survey tool can help you with utilizing your HPC resources optimally. Survey is a broad tool that gives you a lot of different information about the application without significantly impacting the application's performance. We at Trenza have a lot of experience with HPC application performance tools and tuning your application. If we can be of help, please contact us at dmont@trenzasynergy.com or just leave us a message in the comments below. I'll put that contact information in the description of this video. And that's it for today. Thanks so much for listening. If you like this video, please give us a thumbs up and subscribe.